Thank you. Thanks the GIW 2023 community, and thank for the Li Guangqian School of Medicine for the Women in Science to provide me the opportunity to report our work. So today, I'm going to report our work. The title of the project is Genetic Determinants of Women's Metabolic Syndrome. My name is Hong Pan. I'm a principal scientist from Singapore Institute for Clinical Sciences, A*STAR. So the outline of this report includes, first of all, we are going to introduce metabolic syndrome, which is a complex trait as the precondition of the cardiometabolic diseases. Then we are going to introduce, we developed a gene mass, which is a polygenic model for metabolic syndrome. And we're going to introduce the method, which is a cohort-centric machine learning method that we generate this gene mass and examine the gene mass across different age groups, different cohort, and different sex groups, and different disease status group. We are going to show that gene mass can predict earlier disease onset, much more earlier before disease onset. And the association of the genetic metabolic syndrome and with the metabolic status are persistent across the lifespan and across the generation. Okay, so why metabolic syndrome? Metabolic syndrome is a centric multifactorial risk factors causing cardiometabolic diseases and type 2 diabetes. Here is the data from Ministry of Health of the all deaths, principal cause of death in year 2019 to 2021, even include the pandemic COVID. You will see there that cardiometabolic diseases and diabetes account for more than 40% of all deaths in Singapore. Thus, we have the war against diabetes. So, what is the definition of the metabolic syndrome? Clinically, we take care of 5 important clinical measures, which include the elevated fasting glucose and the large waist circumference and the triglyceride, high density lipoprotein, and the blood pressure. For individuals, if you have 3 or more disorders coexistent, you can be diagnosed as metabolic syndrome, which is a precondition of the cardiometabolic disease. And it is well known that metabolic syndrome is an interplay between genetic factors and lifestyle and environmental behavior and all the others. Here, we are working on the genetic factors. So here is the hypothesis that we are working. First of all, we believe genetic determinants of the metabolic syndrome persist across the whole lifespan, and it can help the disease prediction much earlier than disease onset. And genetic determinants work with others can help the population health stratification and precision medicine. Okay, here is the landscape of the project. The prime discovery cohort that we're working is a Singapore birth cohort, Gastro and Espresso. We are working on healthy women, well-developed, but early before disease onset, at their year 20 to 40 years old. We developed genetic gene mass and examine it across different ages. So from middle-aged women to adult people in UK Biobank and ATTRACT, which is another cohort, disease cohort. And from women, the model is developed by women. We will examine it male and female, okay? And we will also work on the different continent, from Asia to UK, and from mothers to their offspring. When we gather all these subjects, the studied subject, together and arrange it by their age, you can see a very beautiful coverage of almost all the life course, from very beginning, from 5, 6 years old towards the end of life. Okay. Okay, here's a quick introduction of the cohort. First of all, is our local prime cohort, Gastro and Espresso. So there are birth cohort, and Gastro cohort is a longitudinal measure from a woman during pregnancy towards delivery, and we follow the measures towards their postnatal and the baby from birth towards now. The eldest baby in Gastro is near 14 years old. Okay, in order to make up a Gastro study, we have another cohort called Espresso for women pre-conception, before pregnancy. So plus Gastro and Espresso, we are working on healthy mother and mother-to-be, which is the discovery cohort in this study. And their offsprings will use as a data set for validation. Okay, the second important cohort is UK Biobank. We all know that UKB is majorly in European, but there are 2% of the Asia population in UKB. If you're taking care of this 500,000 subjects in UKB, 2% is about 10K subjects with full span of the phenotype and the genotype. And this is a very important, precious resource for our Asian cohort validation. Okay, we also work on UKB European cohort. So here, we are using subjects with both genotype and metabolic measures. We also look into their ICD-10-coded electronic records of diseases and lifestyle factors and other factors. The other cohort is a track cohort. It's our Singapore local cohort. A track study is the largest heart failure cohort-based study located in Singapore. The study involves deep phenotyping and genotyping on 2,310 individuals. So we work on the WJ's genotype, their metabolic trends, and the cardiometabolic diseases, case and control. So what is the prevalence of metabolic syndrome? If you ask this question to Google gives you a very quick answer, 25%. But if you ask ChatGPT very hesitated. Before you tell which age group, or the sex group, or the population group, and their disease status, it's very hard to tell what is the metabolic syndrome preference. So based on our study on more than 400,000 individuals, we draw this chart to show actually metabolic syndrome changes. Okay, it's very intuitive and well accepted. Aged people have a higher rate than young people. Diseased people have higher rate than healthy people. And the men is higher than female sometimes. And most important, Southeast and Southwest Asia, like Indian, Pakistani population, have highest metabolic syndrome rate across the subjects that we are studied. So I mentioned we are using, take two very important advantage. We are not go to the GWAS on this very small data set, 1,368 samples. We don't have the power to do the GWAS, but we take the advantage to connect all these existing GWAS for the metabolic traits. So there is no GWAS result on syndrome. Metabolic syndrome, GWAS is not ready, but their single trait is very well studied. And we can easily find a lot of well-studied GWAS on the single trait like WC, blood pressure, HDL, and we accumulate 17 GWAS data sheet and accumulate about 100,000 genetic variants that is reported less or more related to metabolic traits. And we use this as our features. We build up our feature, and we apply this 100,000 SNPs to our genotype, and doing the QC and LD pruning. So our final feature space is 32,090 SNPs. And we use machine learning. It's a very intuitive, naive machine learning like lasso elastic net for the 80%, 20% split, 10-fold cross-validation, and doing the selection. This is our final result. So GMAS, the final GMAS model, based on the discovery cohort study, is comprised about 7,850 weighted SNPs, which can explain the observed clinical metabolic syndrome. In the testing set of the discovery cohort, the R square is 9.70%. Okay, when we validate GMAS into UKB, so UKB we have two parts. One part is Asian, the other part is European. For the Asian, in the Asian female, the R square is 5.05%. It is down to male, which is 1.5%. When we apply this GMAS to attract disease cohort, we see in female we can achieve 12% and the male down to 1.3%. And when we apply GMAS to the genotype of the offspring of the gastro mother, we see in the girls the GMAS R square 7.5%, and we can achieve 4.2 to the boys. Okay, the model is totally lost its prediction power in European subjects. So over here we can see trend on female in Asia. We have a better result in female than in male, in Asia than in European. Here is the association of the GMAS score with the other metabolic traits. We have two columns here. One column is a female, the other column is a male. And we have three rows. Each row is a different cohort, UKB Asian, track, and gastro. You can see GMAS can explain the other related traits like BMI, HDL, and TG, fasting glucose, towards 15% in the R square. Okay, and here is the prediction of disease. Okay, we trained GMAS on healthy women when they are near 20 to 40 years old. Can we use this model to predict 20 years later, which have disease onset? So we tested the disease case and control in UKB and in ATTRACT. You can see that GMAS have the power to predict diseases such as T2D, type 2 diabetes, cardiovascular disease, hypertension in UKB, Asian, and in ATTRACT. And we have this control like COPD and depression to show the odds ratio, the significance of odds ratio. Okay, so just now I mentioned genetics factors and living style and other factors work together to the cardiovascular status. Here we are using a machine learning method, SGBoost, to work on the genetic factors and all the other covariants. Okay, these covariants include age, education, socioeconomic status, physical activity, and the sleeping style. All these factors extract from UKB. Okay, so this is ROC plot to show if we are using genetics risk only, we can achieve AUC 0.85% for the multimorbidity. Okay, explanation of the multimorbidity. So for the co-assistant for more than two diseases coexistent on the subjects. Okay, so for the covariance only, the AUC is 0.69. If we add in gene mass and covariance, we can achieve the AUC 0.71. Okay, so last of the list, let's look at the child. Okay, here our colleagues from Gastro published a paper to showcase the 5 growth trajectory based on the kids' BMI from just get birth towards the year 6 years old. And there are 5 trajectories, 3 normal trajectory, 2 accelerated trajectory, growth trajectory for the obese kids. And from here you can see the gene mass score have the significant higher in the obese kids or the accelerated growth trajectory kids than the normal trajectory. The strength of our study, we are working on the complex traits and working on the multi-eccentric cross-cohort, and most important, we're working on the Asia population, which is underrepresented. The take-home message is there exists genetic signature for metabolic traits in middle life that persist for women throughout their lifespan and in their offspring. Limitation and the future work. First of all, the pool of the SNP candidate from GWAS are majorly from European population, which might limit the predictive performance of gene mass. Second, the sample size. We have only 1,300 plus samples in the discovery cohort, which might influence the robustness of gene mass prediction. And the panel of gene mass include 7,850 SNPs, which might not be the optimal combination. So we are still working on deep learning to enhance this predictive capacity. And last, we need to extend further our validation to other Asian cohorts. We are trying to connect Japan Biobank now and try to connect a Chinese cohort study. This is acknowledgement. I would like to thank the team, the collaborators, the stake owners of the cohort, and most importantly, I would like to thank the participants in the cohort study. That's all from my today's presentation, and these slides are entertainment cartoon I borrowed from the web. Thank you.